Good afternoon, everyone, and welcome to this presentation of OTF Connects titled Using Math Moment to Multiply Math Skills. And today's episode is called Make Math Moment Through Measurements Part 2. And it is Part 2 and also Part 10 of our series of 10 episodes. So it's the last one, sadly. But as I mentioned last week, I forgot to who I was talking, but I mentioned last week that this has been really a very successful series of webinar, and we're going to discuss with my colleagues at OTF to plan another series, and hopefully Cal and John will be back with us very soon. So we'll start working on the next series. So don't worry about that.
All right.
I hope so. Let me start with the quick land acknowledgement that that OTF is asking us to read. So we acknowledge that we are gathered in the territories of various indigenous people, and we further recognize the stewardships of these lands in which we live, learn, work, and play. And yes, so it's the last one of a series of 10. I don't know what we're going to do with our Thursdays afternoon anymore. It's going to be very strange. I know that you will all miss Cal and John terribly, as I will. And I guess the best way to keep in touch with them in the meantime, before they come back to us, is to visit their blogs. And then from there, you can be in touch with them and you can follow their podcast, etc. So there are two blogs that you guys already know, tap into teensmind.com and mathisvisual.com, and I'll invite you to visit them. And then for John, it's the same. He also has two really nice blogs, mr.orisageek.com and mathbeforebed.com. So that's it. I'm going to ask John to jump in and look forward to this last episode of the series. Go ahead, John.
All right. Thank you, Michelle. And you're right, the last one. And
I know, sad.
I know it's been a great series, a great kind of journey that we've been on. And we're going to dive right in as always. But to kick things off, we always like to encourage everybody to get yourself into the chat. Even if this is your first or second one, like we just gave a shout out to Denit, who is joining us, I think, for the first time live. She just found out about it, who we've chatted with on the podcast. So that's awesome. Anybody else, Kyle, you notice that is a first timer?
Yeah, I'm looking through and I feel like many have been, I mean, obviously we're recognizing many of the names as well, but we see like our 9 out of 10s, a couple 9 out of 10s, a 10 out of 10 from Ness there. And Ness usually has her camera on as well. And I don't know if we've heard from everyone yet, because I know Michelle has been with us for the long haul as well. So super excited to see so many friendly, familiar faces, but then also it's always great to welcome a few new friends into the circle here.
For sure. Yeah. So get yourself in the chat. Let us know where you're coming from, what your role is. We got lots of pre-service teachers. We've got lots of in-classroom teachers, but always let us know where you're coming from, but also how many sessions you've attended. They're just keep funneling in here. Jessica, 10 out of 10. Sarah, 10 out of 10. So that's awesome stuff. All right, Kyle, let's get into it. I'm going to, you're going to share your screen, sir.
Yeah,
okay.
No,
all right.
I just wanted to do that to turn Michelle's off there. So I think we're good to go.
We're going to do that thing right there. And
we are ready today, John. You know, we talked about this last week, that we gave 2 full sessions around measurement. Now, the beauty of that, and you and I both know this, is that there's measurement in every strand, in every concept, in every topic, because let's be honest, counting is measuring, right? Like we're counting how many objects are in a set, or whether we're measuring the quantity, the area in squares, or if we're dealing with cubes, counting volume. Like really, it all comes down to counting. So really, we could do anything here, and we're going to be off the hook for measurement. But today, I know you and I both love this concept that we're going to be diving into, something a little more specific with measurement. And it's something that I feel like we tend to, as we mentioned earlier in this series, that as educators who went through a system where it was kind of a procedures first approach to mathematics, this is one of those concepts that I feel that we kind of rush through a little bit. So today we're going to slow that down. And of course, we want you to hold us accountable. We're going to try to do it in a way that's going to keep you curious. Again, the way we keep you curious may or may not be exactly the way we would keep students in a classroom curious. But I will tell you that I actually used this particular task that we're going to use today in the classroom earlier this week. Every time I use it, I have a blast, and the students do too. So we're going to try to spark your curiosity. So make sure you hold us accountable for that. John, what else are we trying to do here?
Yeah, it's a good one for Pi Day coming up too. So the other thing that we're going to want you to hold us accountable for is something specifically to measurement. We want to investigate measurement conceptually. That's something that we have been doing right from episode 1, is exploring math conceptually instead of just memorizing steps and procedures. So we want to make sure we do that here with measurement, just like we did last week, but part 2 today.
Absolutely. And finally, last and probably most important is we do all of this work in service of strengthening our relationships with mathematics. I'm not even going to say repairing anymore, because even if you entered into this series and didn't feel so great about mathematics, I'm hoping now that you feel like actually it's not a broken relationship for you anymore. I'm hoping you're feeling like you're well on your way to repairing, strengthening that relationship with mathematics. Again, to try to promote our own productive disposition. Nothing is worse than us walking into a classroom trying to teach students to love and appreciate mathematics if we don't have that same love and appreciation for the mathematics. So let's make sure we do that. And again, hold us accountable. That is the only way that John and I grow, is to hear your feedback at the end of the session. And we're going to dive right in here and try to keep on going here with a specific task. And before we do though, John, let's bring this up. For those who weren't with us last week, we did look at a continuum of measurement understanding. And you'll note here, Anne Pigeon was a student achievement officer with the ministry for a few years. She had actually introduced me to this idea. So I'd like to give her credit that she shared this with me. And it really changed how I looked at teaching, not just measurement in particular, but pretty much everything, because everything in mathematics has measurement involved. And today I'm wondering if we might be able to highlight some of these different stages in this continuum, from direct comparison all the way to indirect measurement. I wonder where this task is going to kind of land us here today, and where we might be nudging along. So we'll come back to this near the end.
Yeah, it's also I want you to think about also how that progression there, the continuum, kind of mimics or kind of echoes some of the curiosity path that we do with our students, and what we've been doing with you about noticing and wondering through to being more specific with mathematics. So we're going to maybe do some of that comparison too, because I think there's some parallels there.
I love it. I love it. And actually, now that you say that, John, it kind of gives me a little bit of an epiphany as well. Like, I didn't see it that way, but I'm seeing it exactly what you're referencing. So I'm really excited here. We're going to get you started, friends. So noticing and wonder as usual. And I feel like we've all built some trust, like a community here. So we're going to ask that as we share this short little video clip, we want you to feel free in the chat, but more specifically, turn that mic on and just go ahead and share something that you notice or wonder as we go here. It'd be great to hear your voices early in this session. And we're going to dive into some fun here. So let's get to it. Anything and everything goes for those who are new to our session. And we're going to go ahead and share this right now. Let's have a look.
Let them come in.
Ooh. Beautiful architecture and art.
Ooh, architecture.
Who's that dude?
We don't know him.
I wonder if it's a university. Looks like a university building.
All right.
I
I'm hearing some
wonder.
good ones.
Feels like we can feel each step they're taking.
There's the circle we did at the beginning.
Interesting. Okay, I'm jotting down a bunch of these here. Keep them coming, friends. Definitely.
I noticed little tiles around the red part of the circle, or red-brown.
Tiles around
So shapes,
circle,
maybe square tiles.
shapes, square tiles.
Lindsay's saying in the chat, I wonder if this is related to the circumference problem we did before.
Interesting. Circumference problem from
Ooh, I like that one. How many people can fit in the circle? Someone said.
people. Okay. Super cool.
Yeah, lots of noticing of the tiles, lots of little tiles. How many people can fit in there? I
So
wonder if there's some
Walkerville?
sort of symbolism of the circle.
Ooh, is there symbolism?
Oh, I wonder if I see a speaker. I don't know. It's like a on the left side, and I see lanterns and trees.
And the banner, I think, says Walkerville. I don't know where that is.
Ooh, Walkerville.
And
Awesome.
King School maybe, or some school.
I'm actually interested in, someone was saying it reminded them of something we've done before. I'm wondering though, does anyone want to elaborate on that? Any thoughts there? What are you thinking? I'm just
I
gonna
think
go ahead.
we'd use the tiles as the little squares around the tiles as units of measure,
Oh, interesting.
because they were all the same shape and the same size.
The building looks accessible, so
Ooh.
there's no stairs, right? So people can get into the building.
I like that, right through the front door there. Lots of notices, lots of wonders.
So Anne Marie is commenting back on your wonder there, Kyle. She's saying we stretched out the tiles to discover pi way back in, and I'm just adding this part back in episode 1 of this whole series.
Super cool, awesome, and you are absolutely right. We did, and now that you're, to be honest, I completely forgot that we did that all the way back in episode 1.
Hey, it was done on purpose because we wanted to tie it all back together.
Yeah, absolutely. So, and John, as you mentioned, Pi Day is coming up. March 14th is considered Pi Day. And I like to tell people a little story about Pi Day because actually I was born on March 13th. That's my birthday. So there's something I tell students that my mom and I actually don't talk anymore because she didn't hold out for one more day and let me be born on Pi Day. So that is a completely made up story. But
it's okay because my wife is born on Pi Day and I only married her for that.
And she knows it, absolutely. Now, as some of you saw, we definitely introduced this and we brought this out. Now, I'm wondering, can anyone elaborate for us? Because some of you were not here, so I did want to give you a little bit of this heads up. And I'm curious to know, what do you remember from that experience? Because that's going to help us with kind of our launching off point today, because I really want to go back. I want to make some connections to our continuum. And then I want to talk about a few other ideas that we have as well for introducing ideas around circles as well. So anyone willing to share that for us and help us out?
Feel free to just flip your mic on and or do the hand raise, like hit your hand button.
I can't remember for sure, but did we see the number of tiles across the diameter?
We absolutely did. We saw the number of tiles along the diameter. So what I'm going to do is I'm going to share that with you because I do want to kind of make and extend a few ideas here. I'm just going to pull this over here for just a second. And we didn't spend too long on this. We just spent a little bit of time sharing and getting you to estimate. So the first thing we had you do was we had you share and ask, and we actually had you estimate how many square tiles would wrap this particular circle. And you are right. We would then go ahead and share some of, and I want to make sure my right screen is on here because
we're only seeing the notices and wonders right now.
Yeah, that's what I thought. There we go. So here's the square tile, and we went ahead and we actually shared how the distance across, and we slowly increased the number of tiles here all the way across in order to give you this look across the whole circle. And we ended up with a total of 52 square tiles across that circle. Now, my wonder for you to think about is I'm wondering when we use these square tiles, I want you to think back to that continuum that we explored last week. And I'll pull that back up to the screen here. And I'm wondering, can anybody help us try to land us, like whereabouts does this task start when we think about the continuum of measurement and understanding? Whereabouts, again, it is a continuum. So sometimes you kind of land in the in-between zone, or, you know, sometimes I feel like the middle two can be kind of easy to mix up, but let's hear from you folks. Where does that put us when we start measuring with these tiles? What do we think?
Feel free to throw that in the chat, folks. We'll kind of monitor them as they come in. It's kind of some thoughts on which one, and maybe like why that might be the case here. We got a kind of a mixed bag coming in here. We've got some indirect measurement. We got some direct measurement, and also like we've got some reasoning. I think Marcus is saying it's like it's visually accessible, but it's more than an algorithm.
I love it. I love it. Lots.
I had said indirect measurement, but I think I meant indirect comparison.
There you go. Perfect. Yeah, because the indirect measurement, when we see that, is kind of like, you know, me just telling you a quantity with a unit and maybe not even showing you the unit. Like here, we are actually iterating an object in order to get a count. Like we actually have this count. So I would say somewhere in this indirect comparison to direct comparison or direct measurement, I'm going to even say direct measurement because we are iterating it right on top and we're counting it up.
And yeah, we're saying exactly how many here instead of saying like we're just comparing between the two.
So something I want our friends to think about here, first of all, in the Ontario curriculum, first of all, circles up until this current year, we would study these ideas in intermediate, and in particular in grade 8 would be where we would spend most of our time in circle land. But you have to also consider that some students in our classroom might not be ready to be at this stage. So we might even want to nudge them a little bit earlier and give them circles and let them compare and use other tools that aren't necessarily going to initiate a count before they get going. But as you saw in episode number 1, what we ended up doing after you made an estimate was we took this and then we basically helped you refine your estimate by seeing how many of these 52 tile chunks, these 52 tile units, it would take to get around the circle. And, you know, initially, a lot of people like to think it might be double. And every class I go into at all kinds of different grade levels, students tend to give me answers like 104. Some students give more than that, but usually it's like 104 up to, you know, 400. That's like the range. But then as soon as you see this and we start to get students thinking about, you know what, like, let's think about this. Let's pretend this was a big circular park for a second. And I was standing right here and John was standing right here. What would be the quickest route to get there? If I was just walking at the same speed and I had the option to go all the way around the park or all the way across the park, which one's going to get me there faster? And as soon as we give that context, we give that thinking or that connection for students, oftentimes they're like, oh yeah, that does make sense. It's going to take me longer. It's going to take more tiles to get around. And then we can see this build and slowly evolve around the exterior of this circle. Now my computer's giving me the spinning wheel of death, so we're gonna have to wait for it. Yeah, there's a lot of tiles, so the computer's like, I got a lot of work to do over here.
Yeah.
You know, I've already got 104 up there. Here we go. There's another group. And then finally we see that it takes 3 and a little bit to get all the way around the circle. Now, I know for some of you who are with us in episode 1, you're thinking, okay, we already saw this, but I want to stretch your thinking here. Me and John want to get you thinking a little bit beyond this for a second. And you may or may not remember this visual here. When we unpacked this, we shared 3 circles. If my computer allows it, we'll see. It's still spinning. We have 3 circles here side by side. Uh-oh. It's really lagging. There we are. Okay, here it is. So if we take these tiles and we stretch them out, we actually get 3 of that distance across the circle, or 3 of the diameter, we like to call it, and introduce that language in our classroom. And once this shares or shows up on our screen here, we'll get a little bit of a perspective as to the relationship between circumference and the diameter of a circle. And I'm wondering for you, friends, how many folks are feeling like when you look at this, and maybe it might be from episode 1, but when you look at this, does it give you any new thoughts about this idea of pi that we learn in school, we use a lot, and then as you go into high school, you use it even more so if you continue with math courses in trigonometry, in calculus. But did we ever really have an understanding of what pi truly is?
Yeah, this is a good moment, Kyle. Like, I wonder if anyone wants, like, I don't know if we've shared that we had we have a podcast, a weekly podcast, and we talk to many educators every week about memories they've had in their math class. And I actually would love to hear some different memories you've had or maybe didn't have about pi. Like for example, like not pie.
It sounds funny. It just does. Yeah. It just sounds funny, you know, but I know what you mean.
I wonder if we've got some brave people that would like to put their hand up or turn their mic on and tell us like what their first memories or when they remember about, you know, the number pi in their school experience. Because I can definitely share mine, and I'd rather wait and kind of hear from everybody else or hear from a couple on what their memories of pi are. Anybody wanting to share that with us? Because I have a feeling I know what most memories are like.
I just memorized this rote memory. Every time there was a circle, you had to use pi. You had to remember it's 3.14, but your visual kind of decomposes that. I actually said like the 8 left over is kind of 14% or 14 hundredths.
I love it. I love it. I'm trying to see who was.
It was Marcus.
Speaking.
It was Marcus.
Marcus. Awesome. Welcome back, Marcus.
Yes. So that's good. I was just going to read Ness's because I laughed out loud. That she remembers nerds who recited all the numbers and made us feel stupid. People who could just recite the numbers. It was like, I just know pi up to 8 decimal places or 20 or 30 or more. There was always like that ongoing competition that still exists, Ness, in high school, as who wants to compare, who knows the most digits of pi. So I wonder what else, anybody else want to turn their mic on? I think we've got some mics that are on, and we'll let them come in.
And I'm noticing Dunit says it was a lot of fun, but didn't learn much, right? And again, kind of goes back to Marcus's comment. I know that I can relate to that experience. I just knew that it was 3, and I used to say 0.14. I didn't realize that it came from anywhere, even though my teacher probably told me that. I was probably told, I probably wrote the definition down, but I didn't understand it. I didn't know why I was writing what I was writing, you know?
Like, I wonder, like, oh, I see. I was going to ask Danny to elaborate on the fun, but I'm now seeing that she made necklaces. Okay, so yeah, like I think I echo a lot of that, Kyle, and yours as well. Like, I probably was shown that it is the, you know, if you divide these two things, you get this number. But I felt like it was definitely just something you memorized and you just had to use in area and circumference calculations. And that was it. Like, it was not, you know, this mind-blowing thing that I feel like it should be. You know, it should be this mind-blowing phenomenon that in no matter what size of circle you have, that if you take the circumference and you divide it by the diameter, you always get 3.14, and it keeps going on. And it's an irrational number. Like, it doesn't repeat. It's not like 0.333333. It's this cool phenomena that kids should just have their minds blown when you show them that, instead of just saying it's 3.14.
Well, and you know, it just reminds me of how important it is for us to take those opportunities to give students a mind-blowing experience, right? Like, how many times I've learned why something works in math, and I always say mind blown. Like, I had no idea that was going on. And it's like, why not? Like, why aren't we doing that? Like, that would, I think, make so many students kind of lean in if they were like, wow, there's like so many crazy things going on there. And now I know I'm biased. I love teaching math. I love talking about math, but I do think that people are always looking for, like, think of your favorite movies. Your favorite movies are always when there's like a twist where something happens and you just like go, whoa, like, I was not expecting that.
I was going to, you were at the same session I was. We went to a session by Dan Meyer a couple of years ago, his session was all about mathematical surprise. And I think that was the title. And it was like all of these surprises that you normally have in your life that you think are awesome. And I think he compared them to movie surprises like you just did, Kyle. It was like, think of The Sixth Sense. If you ever watched The Sixth Sense and you were mind blown at the end of that movie, that I'm going to spoil this right now, but Bruce Willis was dead the whole time. And you're like, what? How is that possible? And the best part of it, his session was Luke, Darth Vader was Luke's father. It was like, you're like, what? It's like all these mind blowing things. But in math class, we tell kids the surprise before we reveal it. And he had this great image of saying, like, the textbook does this really well by going key featured area or key ideas in this big box. It's like, hey, that's the surprise. We just told you up front what that surprise is. Instead,
don't worry about reading the rest of the book. You know, like the rest of the book, it all comes down to Bruce Willis was dead the whole time. You know, so don't even worry about it.
It's like, imagine this moment. Like, I think I shared this back in episode 1 when we did this activity. Is like, imagine that moment. Like, you have kids draw circles and say, what is draw the most perfect circle you could draw, and do it on your desk, or do it. And you can't use a protractor, or you can't use a compass, or just, you have to freehand draw your circle. And everyone would draw their own circle and then have them measure the diameter across in different ways. And it's like, whoever could measure the diameter and then divide it by the circumference, and whoever's got close to, this number is the most perfect circle. But if everybody drew a different circle and everyone divides those two things, it's like mind blowing that you all have the exact same number.
Yeah, like, how is that how is that even possible? That like you could basically predict that's going to happen. And, I as we talk about this, like, I like this next part, because one of the reasons why I wanted to bring this problem back, and again, I knew there would be a few people who weren't there, and I love the portion that we had already done in episode number 1, but I find even more interesting when we dig deeper. Now, mind you, in a classroom, you don't want to do this like together. Like you don't want to go too deeply too fast. Like you're going to maybe give students, these were the 2 prompts I gave the class I was in earlier this week. I was, notice here, I didn't show the squares, but I wanted to see like who heard what in the classroom. So I was just like, here's this one circle over here. It takes 15 squares to get across. And the question is like, about how many? So I don't want it to be like, 47.38, squares. I want you to go, well, I kind of know that it's going to take 3 and a little bit of that to get around. And one of the students said, for this one, said 47 squares about, but I think it's a little more. And I was like, well, tell me more about that. And, the student went on and said, well, I know that it's going to take 3 groups of 15 to get around. So that's 45. And then right away they said, well, and I know that like the 1400ths, right? If I go like with like a 10th, that's like 10 hundredths. So they said, it's going to be like 1.5 extra squares. And they said, that's at 10. And then like half of that. And, so they kind of like rounded and said about 47 squares. I'm like, how awesome is that? I never once did that in my learning experience in K through 12 to actually realistically break this down and come up with a pretty precise, now I'm going to call it a precise calculation, but where we've rounded pi a little bit. And I just think that work is so important. We can emerge this idea of the diameter. We can emerge the idea of the radius, which you see a question there sitting there. The radius is right there given. We don't have to name it right away. We could be like, wow, that's going to be confusing. Like, do you want to always say like, okay, the distance from one side of the circle all the way to the other side through the center? Like, do you want to say that every time? Or do you want to say like the distance from the side of the circle to the center every single time? Or I wonder if there like could be a name for it. We can even ask students to name it. Like, what do you want to call it? And, you can play with that name, and then you can also share the actual name and kind of work your way towards that. So, there's so many things we can do, but I want to take it further. I'm going to pretend like episode 1, we did all this stuff with circumference. We emerged this idea of pi, and we're like, well, okay, that's going to be really helpful for circles with the circumference. But like, what about a scenario where I was like, okay, how many square tiles would it take to actually fill this circle? And here's what I want to challenge you to do. Like calculators, no dice, like put them away. Also, I want you to take your prior knowledge. So if you're an intermediate teacher, or if you're a secondary teacher, or if you went to school for mathematics, I don't want you to just go to the formula that you know. I want you to think about this from a student perspective who has never bumped into having to deal with area of a circle. And I want you to think of how could you come up with what you believe to be a reasonable estimate. Okay. You're welcome to make an estimate now, but I want you, now that you know there's 52 across, I'm wondering like, what could be some strategies that could give you like a number, that's too high, maybe a number that is going to be too low. And then like whereabouts in between those would you land? All right. I don't want to give too much away here, but I want you to try to strategize here.
Yeah, let's set this up. So Kyle, why don't we do this? I'm sure that we'll give some time to work on how many. So like if you've ever been with us in the past, you're going to grab a piece of paper, you're going to grab your pencil or pen, and you're going to, like Kyle said, no calculators, draw based on maybe stuff that we've talked about or your prior knowledge, figure out how many circles are going to be in there. However, but before we do that, because we're going to put that link back up on the screen. We want to see those pictures, see those solutions. We're going to get them from you by sharing that special link from Knowledgehook. We'll do that in a moment, but let's first get some estimates before you turn to the numbers. Okay. So before you turn to numbers, you're just now eyeballing it and you're starting to formulate some plans in your head.
Yeah, you might even be like doing some sort of like mental math based on what you're seeing, but again, not relying on a formula.
Yeah.
Like there's no formula for you yet.
You got
know,
it.
We don't know what it is.
You got it. So why don't we do this? Why don't we do the waterfall method here on, well, I think we did this last week on the three estimates we're going to do. We always estimate three numbers in our classes. And so give us a too high, but do not push enter yet. Okay. So we're going to give a too high out there. Get it ready, type it in. And when I say go, you're going to hit enter. We'll have the waterfall, all those, what we would call it, a chat explosion.
A chat explosion.
Yeah. All right. So here we go. Get it in there. We're going to hit enter on the count of three. We're doing a too high only. Too high only. Here we go. 1, 2, 3.
All right, we've got all big numbers of too highs. Now here's John. I know we usually like go straight to the too low, but I'm wondering, anyone out there want to give us a perspective as to why they picked their too high?
Yeah, let's do that.
Maybe it wasn't strategic. Like maybe it was just like, well, it just doesn't feel right. Cool.
Right.
What, like if anybody did a too high that was based on something, like tell us like, what were you basing that on?
What's your reason?
If you felt
I had
like
maybe some faulty thinking.
Ooh, I like that.
So I'd split the sphere into quarters.
Okay.
And pretended that one of the quadrants was a square.
Oh, interesting.
Okay.
So what I think I'm hearing, and I'm going to get to test my circle, amazing, perfect circle.
Yes. Nice
drawing.
job.
Not bad. Not bad. Okay. You know,
a little wobbly.
Okay. Tell me what you did. And I want to try to model what you said.
I made 4 quadrants. So
awesome. So kind of like split this, I'm guessing like vertically and horizontally.
Yes.
Okay.
And then, well, it didn't matter which quadrant, but I worked with the upper right. And so I knew the radius, the 2 radii that I have are 26. Like so 26 and 26.
Oh, and here?
Yeah.
Got it.
And so I knew that if I squared those and timesed it by 4, it'd be too much.
Oh, got
and
it.
I didn't know this
you were
square.
Doing like this.
That's the idea. And I knew that would be too much.
Right.
And I worked with 25 by 25, knowing I had lots to spare.
Right.
Oh, I like that strategy. So you're like, why work so hard, right?
So let me go find. Michelle said 2,700 was her too high.
Yeah.
In the estimate. So 25 times 25 being 2,500. And you were like, let me bump that up a bit, or times 4.
Yeah. So I had 25 by 25. I thought was 675. Am I wrong?
Yeah.
And then times 4 was 2,700.
I don't know. That's what I said too.
Okay. And then times 4. So multiply that by 4.
Okay.
Right. And I did a little algorithmic multiplication there, but.
Awesome. I'm going to do like, I'm going to try to break this down like a student. When I'm with a class, I try to break it down in a creative way to see if I can help them out. So I'm thinking like, well, if I know that this number right here is, I like 500. That's fun. I also like 100. That's fun. And then maybe 75. I like that. So I know that 4 of those is going to be 2,000. 4 of those is going to be 400. And then this one's a little harder, but I know 2 of those is 300 plus another 2 more is 600. Okay. So is this like 3,000? Am I right? Or did I mess up? Do I feel okay? Whoops. I don't know if I showed everybody.
There you go. Now we can see.
Ta-da.
All right, good. All right, so that's some good explanation of too highs. I'm just going to scan a couple more. We've got Dora is saying similar, did 52 times 52 for the square. So I knew it would be less than 2,704.
Oh, so can I just model that for a sec? Because while it's the same, it's not. You kind of did it the opposite. Like here, we started here and iterated. And then what I'm hearing you say is you were like, no, I'm going to do this all at once. And you found this square. Am I right?
That's what she,
52
I think
by 52
is saying, yes.
And kind of the same idea, right? So it's like, we've got this issue here. And like, I don't even know, like I've had students do this as well. Like if I look at this, just at that square right here, when I look at that too, I have the conversation often with students like, this area here, is it more or less than half of that circle or of that square? And most students are confident it's going to be more, right? Like this would be half. So it's going to be more than that. So it's like, okay, is it like 3/4? Like, what is it? So that's a great way to kind of help with our estimates. I'm wondering, John, what about like maybe some too lows?
Yeah,
like,
let's move to a too lows. Okay, so get your too low in there. Get your too low, and then we're gonna hit enter on the count of 3. Too low answers, only wrong answers coming in. 3, 2, 1, go.
Looking for my.
Got a couple. Got 52, and as a too low. 500's a too low. Even 1,000 we have is a too low here. And 899, 1,800. It's almost like now that we've got some reasoning out into the open, you can easily go, now I know a too low is maybe one of those quarters or half of that circle, or like 52 is even, definitely a too low. And we always want to push our kids to be risky with their too lows. Like, how risky can you get? Because then that will bring out the thinking, this thinking right here. So those are all some good too lows. And at this point, it's almost like we could go to an estimate right now, or we could switch, because we've got some really good thinking out into the open right now. And I think it might even be a good moment to head to your page and start to kind of get even more precise, because now we've actually shared some strategies.
John. Yeah. Like I'm loving these ideas, and I'm curious if anyone can maybe, like, if there's anything that you can do creatively. And I wonder too,
we'll leave it open to you guys.
Yeah. Do whatever you need to do. Maybe you want to do a different circle with different measurements, if that's going to help you too. Like, is there like a pattern that you notice? Like, what's going on?
Yeah.
We'll like people really like squares, which I don't know about you. A lot of people call me a square. I enjoy working with like rectangular-y type stuff myself. So I love how people are kind of going to things they know. I wonder if we can use that strategy at all here.
Yeah. So why don't we turn our mics off, turn our cameras off. We're going to leave it to you folks for probably a good, like this is going to take some time, I think, Kyle. So some minutes here. We'll get that link up on the screen.
Yeah, firing it up.
Our Knowledgehook SnapShots tool. If you're new to that tool, Kyle's going to put a link and a code up on the screen. I'm going to type it in the chat. And what you're going to do is, after you're finished with your strategy and your solution and your thinking, you're going to use your phone or your mobile device to take a picture of wherever you're working. And you're going to go to that link, joincage.com. You're going to put that, there's a code he's putting up. It's just behind you, Kyle. Just make sure you move it into the middle.
Oh, darn. I should never write on that side, eh?
And keep going. Oh, there, you're out of the way. So you're going to type that code in, and then that will allow you to kind of link us all. They'll link us all up. You're just going to guest log in. Just hit the guest button, put your name in there, and then a button shows up, and all you got to do is hit that button to upload or pick your picture to send to us. That'll automatically be beamed to Kyle. And then what we can do is we can look at those solutions as they come in, and then we can do some selecting and sequencing to keep our discussion going. We're driving some curiosity. We're allowing kids to play here with math. We're allowing you to play here with the math to develop some strategies, because we're going to try to link your strategies. Most of you already know what the area formula is, but we're going to show you how to link your strategies to building the area formula.
And the last thing I'm going to say before we turn our mics off and just go silent for a few minutes is, if, let's say, you're confident in how to derive the formula, so if you have that experience here, I want you to think like a student. Like, what might a student do? If this is like your first time exploring this, then of course go at it just from your own perspective. But we want to make sure that we can maximize this experience for everyone. So definitely give it some thought. And Kathy, I project the background. We are using a software called OBS Studio. It's free software. John and I are geeky. We enjoy it. but I also have a document camera, so I can kind of switch between the two on the fly here. So it's independent of Zoom that we're doing this. But we'll go silent now. And if you have other questions about that, of course, don't hesitate. All right, we have a few ideas coming in. And again, we are not looking here for perfection or for a precise answer necessarily, but more or less we'll call it more precise estimate than your high and low, of course. And whatever your prediction was, like what might be a good way to get closer. And I'm really curious. Oh, I'm seeing a few other really cool ideas being shared as well. I'm just tossing them into the slides right now. So feel free. Don't be shy. All right, John, are you there, my friend?
I'm here.
Okay, we've got a few coming in. If you're still working, feel free. You can always still submit. No rush at all. I'm just going to share here a few of the submissions. And of course, if you feel like sharing some of your thinking, that would be fantastic. We always love that. So let's have a look here. Here is one of the ideas shared. I want everyone to take a moment to have a look and see if you can try to make sense of the thinking here. And then we'll have one of those people maybe share what they're thinking, and then we can go to the the author of this solution and try to get their perspective of like what they were thinking here. I have some assumptions I'm making.
Yeah.
I'm curious to see whether it's true or not. So we'll give you a minute here to think this through, and then we'll share. All right. Any thoughts out there? What are we thinking, friends? What do we see? I'm curious. Anyone willing to try to share a perspective of what this particular mathematician was trying to do here?
Diameters. It's a tough one.
And one thing, like, I'm going to share what I'm kind of thinking is almost like an approach where we can see the tiles wrapped around the circle, and they've kind of broken that up a little bit into, we did 52 twice, and then there it's split up over here. And then also it's almost to me looking like an attempt to maybe count these diameters. Like if you were to count all the diameters starting with each of the tiles and make it all the way across the circle, that might give you a good place to start. Over here, it looks like a full square, right? A full square of 52 by 52. And then this strategy over here, it looks like it was added together, but then also it says at the bottom, overlapping tiles too high. So looks like this might be the too high. And I'm wondering if maybe they're landing somewhere like in between here, or something like that. I thought that was kind of an interesting approach. Here's another one. Might be hard to see this one, but again, kind of counting the number of diameters they could make. You can see how this circle is cut up and trying to count those diameters and then making an estimate from there. Looks like 2496 or so, 2086, something like that. It was really fuzzy, so hard to see, but definitely an interesting approach as well. And then
that one.
Have a look at this one. Now, John, do you want to take a stab at what might be going on here? And again, we would want to talk to the student, talk to the individual to ensure that we're not misinterpreting.
So what I can see is they use the strategy we did for our too high, and was look at there's a square here, and it's a 52 by 252 square. We already saw that 2,704 was a too high on our estimates. And now I'm seeing if the area is 3/4 of that full square. So that part is, I guess, is that an estimate is of the square, 3/4 of the area, or the number of squares that would be in there. So then they got about 2,100 here as their area is close to 2,100. Interesting stuff.
Yeah, lots of really interesting ones. This one came up a couple times, so I'm gonna actually, this one didn't come up, but I'm curious about it. It just showed up on the screen here, so I'm gonna pull this one. Here are a couple. I'm just gonna hide names, and this one I thought was kind of interesting. It caught me at first glance here. There's almost like here taking the same circle and inverting it to try to see if that would help at all. So that one's really interesting as well. Like, all of these are super interesting approaches to trying to solve this.
I got one more. I don't know. Is there any more there, Kyle? Or
yeah, here's one here. Okay. This one, I saw this come in 2 different times, like putting a square inside the circle, I thought was pretty cool. I'm wondering, I think I know who it was. Does that individual want to share like your thinking here? Now, I also want to make sure that we don't assume we know a formula. So I'm curious if how we might be able to break this down if we didn't know a formula. Is there a logic here that we might be able to lean on at all? I'm curious. Any thoughts? Maybe not. All right, I'm gonna flip back. Or is something coming into the chat?
No. We got triangles. Lindsay's got triangles here. Now I've got a strategy I was working on while everyone was working on one, Kyle, because I'd never, I was thinking of maybe trying this a different way. Have you shared all of them so far?
These are essentially the ones at least the last time I just checked. And I was going to flip back to the document camera to kind of maybe challenge everyone to think about something. And this would be where what I might ask students to do next. So they've come up with all these ideas. We reshare these estimates, which is fantastic. And then I might ask them, like, a lot of people defaulted to squares, right? In some way, shape, or form. And even, we saw, like, even here, like a square inside the circle. It's like we're fascinated by this idea of squares and rectangles. And to me, it's like, wait a second. Like, I wonder if there would be another way that we might be able to create a square out of this. I'm going to put it to everyone else. Like, is there anything else that we could do? And like, I've got myself a brand new circle that I'm going to try to like model whatever you share. I might even cut another one just in case other people have other ideas as well. But I'm really curious about this. Like what might we do to like take this area of the circle and like make it more like something that we know how to handle? Because I don't know about you, but circles are kind of hard.
Right. And so that's kind of, I think I know where you're going to be going, but I don't think I saw this solution from anyone else, but I was working on triangles.
Ooh, tell me more.
I'm just going to share my screen on the background here. I was just doodling. So this was just me just thinking about triangles for a moment. So I'm going to unpin you.
Yep.
And I'm going to pin me. Pin. All right. And now I'm going to share my screen. So I'm just going to walk you through what I was thinking, which gave me about a 2100-ish. Now I cheated a little bit. I did use the calculator. However, I was going to use my area model over here to do the multiplying. I just didn't get there yet. But I will kind of explain this. I drew a triangular section here in my circle. And I said, okay, the height of that triangle is the radius. And why I'm approximating it because it's actually not. Notice the height only goes to right there.
Yeah.
Which is not all the way. So, but if I look at one tile, so this is why I drew a second triangle over here to kind of illustrate this. If that was one tile right here that I'm showing, there's a tile, then that tile is let's say the base of that triangle, and then the height would go right to that tile, and that would be again the radius 26. And so what I thought is the area of one triangle is base times height divided by 2. And therefore I would do 26 tiles as its height and 1 tile as its base. And I would divide that by 2 and get 13. So I think 13 tiles can fit in this little sliver of a triangle. And so then I said, hey, how many tiles around the edge of the circle are there? Well, that would be the number on the circumference. On that would be 164 tiles. Oh, we did that on episode 1. And Kyle's got a slide there that would show you that if you wanted to do 3 times, the diameter, you get about 164, a little bit less. And then therefore I said, hey, there are 13 groups of 164, which is 2,132. And I was going to come over here and do my area model to multiply this. So that was like, I would get basically 164 slivers around my circle. And then you can generalize this too, but I'll do that maybe later, Kyle, if we have time to show you the formula actually can be built using that technique as well.
Yeah, we'll definitely do that. Like, I'm curious, is there anyone out there in the chat, or turn your mic on? Like, are you feeling John on this strategy? Like, are you seeing
any questions
the logic
about my strategy here?
Because like, I'm looking at it too, John. Like, I could think about it. It's like, it seems like the wider the base of your triangle, the more imprecise you'll become, right? Because like that, like you can kind of see it where, there's that
this wrapping.
That gets bigger and bigger. So if I did like only 4 triangles, then I'm in trouble. That's kind of what, we kind of ran into the same problem with.
You got to do a triangle for every unit around the edge of that circle. So if that circle is measured in centimeters, then you have a triangle every centimeter. If that is measured in meters, then you have a triangle every meter, and that will help you be a little bit more precise with the numbers.
What a cool approach, because John, like the way you've done it, you did it through this logic of triangles, and then the way I was thinking of it, which is different. But again, like this is the beauty of it, is it's all perspective, and it's all kind of what comes to mind for you. I know for me, and I'm going to throw the document camera on here. Like for me, when I looked at this, so like John, his little chunks basically are 13 tile chunks basically. And then you said you had like 164 of these chunks in total. Something that's also cool is like, imagine on the other side, John, I thought of this as you were talking, but I was picturing like, there's going to be like a mirror image,
Ah,
right?
yes.
Oh, this is not the same size as that, but you know what I'm saying? And it's like, well, if this is 13, then it's kind of like, I could like
You could
take
split it in
this
half.
and yeah, I could say, well, like I only need half of them and they're 26 tiles. So that's
Right.
like another way we maybe cut down on the multiplication.
Yeah.
Now, what students might do, like if we think back to this continuum idea, everybody wants to go to like a shape that they know. Like everybody feels good about squares. They feel good about rectangles. John felt good about triangles. But remember, a triangle is simply taking a rectangle and cutting it in half, right? Like if I cut this in half, I get 2 triangles, right? So it's like, there's your half times length times width right there, right?
Mhm,
Like that's where your formula for triangles comes in. I'm not going to dare try to fold this correctly because that's going to be really hard. But if I do, you'll see it. Like, look at that. I've got the same. Oh, it's kind of
too bright or something.
Oh, well.
Yeah.
Oh, there it is. You can see it. Nope, not anymore. Anyway, you get the same triangle on both sides. So it's like the area of a triangle formula is the area of a rectangle formula. We're just going to half it. Okay, so now I'm like, well, John's saying I can use triangles to do this. I wonder if I could take like a circle and I wonder if like there's something I can do to like make my life easier. And actually there is, like a student could take this and go, you know what, like it's not going to be perfect, but if I go at, like I got semicircles, and I don't know how to do the area of that, but if I do this and I go, well, let's see here. If I go and I do this, it's like, you can kind of see John's idea emerging here, except the only difference that I'm going to play with is I'm going to go like this and I'm going to go, well, wait a second. Let me just keep cutting these.
So you're making the triangles out of that.
Yeah. Like I was picturing it kind of like, you know, pieces of pizza, but like now I'm seeing your triangles through your explanation, which is pretty cool. And it's like, as we do this smaller and smaller, like the cool part is white paper is not going to be super helpful for this, but I'm going to do it this way. Like if I take all these triangles and I start to break them down and it's like, okay, well, these ones were across from each other. If I do this,
ooh, look at that.
oh my gosh, like look what starts to form. Now, I'm hoping you can see, like if I get these to the size John was talking about, John was like, you know what?
Yeah, if
Let's
you make
these even
you want it to,
smaller.
You want that base to be 1 unit long.
Holy smokes. And when I do this, and
I'm
cutting that out because I want to make sure everybody realizes in the classroom, we want students to be experiencing this, right? We want them to actually create it. But if I was to take this same circle here, and again, we take this idea and we're like, okay, well, like, let's make John's triangles. There we go. That's not that helpful. But like, watch what happens when we do this a little bit more. We're like, all right, how about now? We're getting somewhere, right? I don't know if you can still see this though, like keeping in mind, like here's our circumference.
Right, it's too rounded still.
Outside, yeah, it's too rounded to be accurate. Okay, let's keep cutting these. Check it out. Oh, we're getting pretty close.
What if we look like, folks?
Let's keep going.
Ooh, that's
okay,
pretty.
So you're telling me like that's not good. This is better. This is better, and this
can make it better.
Would be bestest, right? So if I could even like, we can outdo John's scenario if we could even go less than a tile and make it like super flat. Like this is like calculus, right, John? Like this idea of limits and like, you know, approaching infinity and all this. It's like, if I zoom in, I'd still see some roundedness there on the outer edges.
But it's how precise is your measurement system, right? So it's like if you wanted to use centimeters, you could still make this very, very precise. But you're talking about a circle having an infinite amount of sides that you could decompose into small triangles.
So here's what I want everybody to think about, okay? Because like we know a lot about this this particular circle, right? We know that it's 52 tiles across, right? John, you had confirmed or reiterated for us that it's like 164-ish tiles all the way around, right? Like we saw that there. There's the 164. If we just wrap it around the tile, it'll look, you know, a little bit more like, Uh-oh, computer.
What did it do?
There we go. It took a while, but there it is. So you could see those 164. My question to you then is the following. What are the dimensions then of this rectangle? And I want you to think about that again, okay? So I'll give you this look. I want you to think, I got 52 is the diameter all the way across the circle. I got 164 all the way around. Where does that help me with trying to find the dimensions of that rectangle right there? Because remember, like I'm literally cutting this thing out, right? Like I'm literally trying my best to cut this thing out and make this into a rectangle. It's just not as precise yet over here. So I want you to think about that. I wonder if we could do this like and pretend like we did it, but not actually have to do it, right? Like that's kind of like what math does for us. It's like, well, you don't even have to cut it. I trust that if I cut it, here's what's going to happen. I wonder, can anybody help us with that? What's that going to look like, sound like?
It's interesting because what's going to pop out of this is a little different approach. Well, obviously it's still being made into triangles. However, when I did the area of one triangle, I took the radius and divided that by 2 to get the area of one triangle, because the height of that triangle was the radius, and then I divided that by 2 because that's the area formula of a triangle. And I used 13, which is half the radius, and I multiplied that by a full circumference. Whereas what's going to pop out of here is, I'm seeing there, Anne-Marie has said it's 164 divided by 2, which is 82 for the length, and then multiplied by the radius, which is half the circumference across the length, and you have a radius as the width. And that's a little different than what I had, because I was multiplying 13, which is half the radius, times 164, which is a full diameter. So you get the same number, but 2 different ways to think about those calculations. Pretty cool.
That's super cool. So you were saying like it's half of this. I'm wondering, can like
this is what Anne-Marie has said.
Yeah, Anne-Marie, like, can you help us, like, why half and not just like 164 here? Like,
well, I looked at your picture, and the outside would be the circumference. So that would be 147 a quarter, or it's 164 is what John said. So we need the top plus the bottom is 164.
Right, because you split those triangles up. You took half the triangles are this way and half the triangles are this way.
Yeah, and like check out, I don't know if I changed, you can see it. Check out these pieces. Like I'm going to keep everything where it was, but I'm just going to rearrange the pieces, but keep the tiles where they were. So you can see the colored tiles around are the circumference. And look what happens when we rearrange these pieces. Half of them are on the top, half of them are on the bottom. And then what about the sides? Like what are the dimensions of the sides going to be? Like what are those going to be? Wondering, anybody out there?
The radius.
It's going to be the radius, right? Not the diameter. Because again, we've taken these pieces and like John did one piece. It's like here we're taking the piece and we're like gluing it to another piece. So we're only making it to the center of the circle. So holy smokes, we have an area formula here that we've decided, like we know that that's going to be the circumference. Like we know that. So it's like, it's 164 tiles, but it's shared equally amongst the 2 sides. So that would be like, we're going to use partitive division. We're going to like chop it in half into 2 parts, and we're going to give half, one part this much and the other part that much. So you've got that taken care of. And then the sides, we're going to just use the radius. Now, my wonder is like, can anybody help us with like, what can we do to try to like make this into a formula? Like, I know we're coming out with the numbers here, and I'm feeling pretty confident about that we're going to come out with a pretty close, precise number of tiles. But I'm wondering, like, how can we generalize this? Like, what is it that we're actually saying? What are we doing here? Like, how can I put this into words so somebody else would be like, oh, I can repeat this process?
I think, Denny, I think we're safe to assume that we've already built the circumference formula at this point. So if you're trying to make a formula, we can use the circumference formula to help do that.
Ooh, and I'm guessing because, like, we know the circumference is used on two of the sides, right? That makes sense. Totally. All right, so let's do that. So I think we are all in agreement that, again, we're going to take the circumference, we're going to split it in half. It's going to give us 82 tiles on each side. So we have the numeric value. What is the circumference again, based on our exploration around the circle from episode 1 and then today continuing that? What did we do again to find the circumference? Wondering. Shoot, what did we do? Darn. I can't remember.
3.5 times the diameter.
Awesome. So we took 3 and some, right? 3 and some. I think it was like 3 and
0.14.
Yes. So 14 hundredths. That was like our approximation, right, of that relationship. It's a never ending, non-terminating decimal. Just keep going. But we kind of truncate it down to that point. Awesome stuff. So I could say it's like, basically the circumference is like this 3 and 14 hundredths, or this thing we call pi. And we multiply it by the diameter. But in this case, so I'm just going to rewrite that. In this case, like our side lengths are half of that. So is everybody cool with that? Like, we see it's like half of the circumference on both sides. Like that's going to be our length here. Now I'm wondering, does anybody know, like, can somebody tell me what is half? Like, can we do this a little better? Like, I see half of this number. I wonder if there's a way that we can clean that up a little bit. Like, in other words, what are we doing there? Yeah. What do you think?
What's half the diameter, folks?
So half the diameter.
Here we go. Marcus says the radius.
I love it. Check this out. Half of the diameter is the radius. So now I've got basically, holy smokes, I've got this 3 and 14 hundredths times the radius, because we're like, why do diameter divided by 2? Like, that just feels like a lot of work. We know the radius is half the diameter. So let's put that there. And we know that answer here is 82. Like, we already know that, but we're trying to generalize. And you folks told me that the diameter was split in half on either end. So it's like, we've got essentially, I just heard you say, like, it's half the diameter. So that's another radius, right?
You got another radius right there as its width.
I feel like it's my computer trying to pace me tonight, because it's like I'm trying to click to another slide, but it's just not doing it. So I'm going to give that a second here. But we've got radius on the other side. So now my wonder is like, what can we do with this in order to figure out the area? I've got this big rectangle. I know that my dimensions are essentially the width is the radius. The length is pi times the radius. What are we thinking here, friends?
We've got
what are we thinking?
If I look back up in the chat here, we've got some folks were already kind of on this
train.
Yeah, like in Intel said half the circumference times the radius. So you're looking at your pi r times the radius. And then Michelle's written the formula pretty much, right? You've got pi times r, length times width, folks.
I love
pi
this.
times r times r. Anne Maria just said that too. Pi r times r. Boom. What is pi r times r, Kyle?
pi r times r is the same as pi times a square with the dimensions of r, which is pretty awesome. Like if I actually kind of look at this in particular here, we can actually see the pi-ness of these numbers of squares. Cause like, I don't know about you, I knew this formula was pi r squared. Now, mind you, a lot of people confuse them or like, that's either perimeter or it's area. Like, there's always this confusion, but right now it's like, we're helping to see that it's like, no, there is no confusion because look at this. If I go 26 tiles by 26 tiles, I can like see a square there being formed. Like, I don't know if you see it, like there is a square right there. And guess what? I got another one of those squares right here. There's like a second one there if my computer will allow me to progress, which it may not. And then we've got a third r squared. So you can actually like see these squares being formed. And then don't forget about that little extra at the end. Again, that 1400ths of a radius, which is in this case going to be about 4 tiles or so. So the whole purpose here is, again, kind of thinking about this continuum for measurement and trying to essentially bump into how the area of a circle actually works. So we can actually see it here. And by golly, if we go ahead and actually count up all these tiles, my friends, I'm wondering, did anybody update their estimates, update their precision on their estimates? What are we ranging from here? Like, what are people feeling now if we were to build it from here? And I would love to do this step by step, but if I click another slide, it might give me a hard time.
I was doing it on my computer as well, Kyle, and mine is also spinning.
I think it's because there are a lot of squares on the screen, as you could probably see right now.
Yeah.
So if you work this out and you go, holy smokes, like that's a lot of tiles. We're looking at like 2,100 and what would it be? 32 square tiles.
You got it.
Holy smokes. That is a lot of square tiles. Now, the crazy part is, again, John and I have said it so many times, we both went to school for mathematics and I never into post-secondary for mathematics. And I never understood why this formula existed, how it existed or how it worked. And I'm hoping that you're seeing that here. Even if you're a PJ teacher, I'm hoping you're seeing the importance of the conceptual, regardless of the age range that we're working at. It really, truly is so important for students to see that.
Yeah, this is another surprise moment for sure. And it was for me when I pieced this together. And it wasn't too long ago that this, I'm sure it was working with you, Kyle, on some of this work that it actually is so mind-blowing to look at. Like what you're seeing on that screen right there is you're seeing the area is really 3 and a bit squares, right? Pi r squared is 3 and a bit groups of these squares made of the radius, which is pretty cool, pretty mind-blowing. This is like Darth Vader revealed as Luke's father moment, right? It's like, boom, that's such a connection to other, area of rectangles, parallelograms, there's so much connection happening here that we would just throw that formula down. And I threw that formula down with my students so many times. Pi r squared, that's the area of formula. Move on, let's go. It's just, mathematics can be so much more than what we have done I have done in the past.
Absolutely. And I don't know about you folks, but I'm looking at the time. We are running late on time, or actually, we're actually pretty close on time. But I'm hoping that you're seeing, and throughout this entire series, able to see us working through this 3-part framework in order to help us reveal some of these wonderful surprises, as John mentioned, and Dan Meyer so eloquently puts it, that every single thing in mathematics happens for a reason. And if I'm teaching something and I'm not sure why it's happening, I'm now stopping myself and thinking like, I need to explore that, because there is really no huge value in me sharing it if there's no understanding underneath, because it's likely going to kind of drift away. It's going to fade away like footprints in the sand. So I'm really, really excited that we got to spend so much time. John, I thought with 10 full episodes that we would be like, wow, like there's pretty much no more math to talk about, but I feel like we're just getting started here.
Right.
And
We could
I've
keep
had
going.
nothing but a pleasure working with friends. So why don't we ask them to hold us accountable here, John? What do you say?
Yes, let's do it. So we set off, as always, 3 big things that we wanted you to get out of this. Give us a yes in the chat if we hit these. Here's the first one. Did we spark your curiosity using the curiosity path so that we can engage you, but also so you can engage your students? Hopefully we did that.
Hopefully.
Looks like we did some of that. Yeah.
Awesome
what else?
stuff. How are you feeling about measurement conceptually? And also, it's the last episode. How are you feeling about mathematics conceptually? At the beginning of this journey, for those of you who have been with us for more than a handful of episodes, I'm hoping that, you know, your understanding of what understanding math really is has been shaped a little bit, because I thought when I was teaching for so many years that I was teaching conceptually. I thought that, and I only realized like over a decade later that I was really teaching procedures and memorization and steps. And now I see truly the true beauty of mathematics. How are you feeling about that? Do you feel better about concept-based mathematics? Let's hear it in the chat. How are we doing? Looking good?
Yep, we're looking good. And the last one here, folks, is something that we are trying to do, and the real focus of this whole 10-part series is to strengthen and help repair or become more comfortable with mathematics ourselves so that we can do that with our students. So really hoping that that came through here for you. We want to make sure that you're feeling comfortable. You have to understand the connections in the mathematics so that you can then help your students understand those same connections. So we did that through a number of different strands here for the 10 episodes, and in particular, the last 2 being on measurement. So hopefully we did that here for you. Give us a yes in the chat if we had hit that one. Not just this one, but all the way through. We're hoping that came through.
I love it. Lisa's saying, helping our students realize that they are budding mathematicians. I love it. Every single one of us are. And finally, we're going to be handing it over to Michelle for the last time in this series, but hopefully not the last time ever. Hopefully we'll be able to put something together in the future with OTF, an amazing partner for Ontario teachers and pre-service teachers. And you know what, Michelle, you get to also select someone's big takeaway for our very last Academy membership that we're going to hand over, and in order to work with some of these wonderful friends inside the Academy.
Fantastic, really perfect, guys. Really loved it. I mean, all the sessions have been great, but I think that we will all agree that you kept the best one for the end. It was really, really excellent. We really enjoyed it, and all the comments at the end are really positive. And it really makes me feel so good when I see that people are really benefiting from these webinars. Just want to share quickly my screen again, if I can take it over from you.
Absolutely.
Because I was looking while you guys were giving, I was looking at who holds the world record for remembering the most digits of the pi number. And believe it or not, it's a Japanese engineer called Akira Araguchi, and he managed to reach 100,000 digits.
That's crazy.
Memorize and recite 100,000 digits, and he did that for 16 hours. And after 16 hours, when he reached 100,000, he stopped. He could have gone longer, but he stopped after 100,000. And I can't remember what I had for breakfast this morning. So, I find that absolutely unbelievable.
That's actually even a great math problem itself, Michelle, is like, how long would it take a normal person to recite 10,000 digits, just any digits?
Even reading them. Like
just reading digits out loud. How long would that take? 16 hours. That's crazy.
Yeah, 16 hours, which means that without drinking, eating, I don't know he did it. Anyway, it blows my mind completely. But I want to say it was a really fantastic session for the last one. I want to take the opportunity also to thank all the teachers that have participated in these 10 fantastic sessions. I'm a teacher myself. I was a photography teacher in Belgium many years ago, but I did all my career in digital imaging and medical imaging. And I started working with OTF 4 or 5 years ago, and starting working with teachers again. And what amazed me after working in the industry for many years is to see how dedicated teachers are. I mean, they go far beyond the stricter census job description that they receive, you know, and it really is obvious when I run these webinars with all of you to see how dedicated you are or enthusiastic you are. And of course, Kyle and John, you know, what you're doing is absolutely fantastic. We really love it. And we look forward to starting again in a few months with another session. So what I'm going to ask everybody now to do, if you want, is turn on your microphone, click on your unmute microphone, all of you, and maybe your camera if you want. And let's give Kyle and John a big hand of applause. Okay, let's put our hands together.
Wow, you're too kind.
Thank you very much. Thank you.
It's been fantastic, everybody. Honestly, we've had a blast. It's going to be, I don't know what we're going to do with our time on Thursdays after work.
Yeah, something.
We don't know. We don't know what we're going to do on Thursday. It's going to be really hard.
We don't know either.
I'm going to start talking with my colleagues at OTF straight away and tell them how positive these sessions have been. And we're going to plan another series. Lindy Amato, she's in charge of that. She told me that we may have some budget for the spring. So maybe in the spring, we're going to come with a new series of webinars. So go to the OTF website, check the calendar, and hopefully I will see you guys in the spring. Okay?
Awesome stuff. Thanks so much, everybody. And we had a blast, as always, in this session and all the sessions. So thanks, everyone, for coming. All of you, even though for your first time or your 10th time. So thanks so much, everyone.
Absolutely.
Thank you.
Take care, everybody. And I don't think Michelle actually selected.
Oh, yes,
winner.
it's true. With
all
of that, I forgot.
You get to do that, my friend.
Okay, so let me choose someone. Okay, I'm looking at Janice 01. I'm just picking up someone, Janice 01. I don't know if she already.
All right.
She's still in the room or not.
Janice. So Janice, like if this is your first time with us, then we are going to hook you up with a year inside of our academy, which is we've got all of our these mini courses that are like the 10 sessions we just went through, but also we've got more on lots of different topics. So all you need to do is email us or connect with us. You can go to, Kyle just put a link in there, makemathmoments.com. There's a little blue button in the corner. That's just a chat widget that will send us an email. If you type in there and let us know your email and name, we'll hook you up. But thanks, everybody. Thanks. So much.
Thank you.
It was
We'll
a great
see you
pleasure
later,
working
everyone.
with you.
Have an awesome evening, and we will chat soon. Take care.
High fives for you.
High fives for
High
us
fives
and
for
high
you.
fives for you. Awesome. Have a good one, friends. We'll see you soon.
Thanks, Anna Maria. Thanks, everybody. Bye-bye.
Bye.
Thanks.